Hello, everybody. This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. Today, we're looking at a screencast called Boxed In, or Maximizing Area of Rectangles with a Constant Perimeter. In Unit 4, Topic 1, students learn to model quadratic relationships with expressions by exploring patterns and connecting to area. Key ideas include that quadratics and quadratic functions can model changing areas. Helpful skills. At this point, students have learned multiplication can be modeled as an array of length versus width. This is done extensively in elementary school and in Math 6. Algebraic expressions can be used as models of patterns. This is done in IM or Math 8 and Algebra 1. Maximizing area within a constant perimeter is a common mathematical task. Here, we will focus on doing so with rectangles. Typically, we can begin by asking students to draw 3 rectangles. Each student must draw 3 rectangles with a total perimeter of 40. Draw at least one with a fractional length 3.5, 2.1, 11.8, etc. We're not going to tell students at this point that those fractional lengths are only there to serve a conversation and will not be included in our table of values. The reason for including fractional lengths is to get students to understand that the variable for length and the variable for width are continuous and that they will not be discrete values. But we only want the integers because the integers are going to help us reveal patterns in the table of values and build the expression. Students may draw a 3 by 17 rectangle. When students draw this, it's important to encourage them to check to make sure that their rectangle does not exceed 40. A frequent misunderstanding is that students will do a total of 40 for the length and the width and not realize that their rectangle actually has a total perimeter of 80. Some students may quickly go to a 10 by 10 or a perfect square. That's fine, but we want to get a variety of answers, which is why we want students to draw more than 2 rectangles. They may include something like this 1.5 and 18.5, and that's fine. Again, we want to emphasize that the variables for the length and the variable for the width are continuous. Now let's start building our table of values. Students are unlikely to come up with 0 by 20, but it's what we call a degenerate rectangle. And while it's not something that students may develop on their own, it is important for revealing patterns within the table. So we're going to go ahead and include it. They may include 1 by 19, 2 by 18, 3 by 17, and so on. Notice that I've stopped at 10 by 10. This is because the moment I go beyond 10 by 10 to 11 by 9, I have a unique rectangle. The length and the width are different from the one above 10 by 10, but the area of those 2 rectangles is going to be the same. So I've exhausted my unique areas. There are a couple of questions that we want to ask students as we're exploring. We want students to know or to develop an algebraic expression that can be used to describe the length. We want students to determine an algebraic expression that can be used to describe the width, and we want to do so in terms of the length. We also are going to clue them into an important observation. What portion of the total perimeter is represented by the constant that we develop in our expression of the width? So let's take a look at that first question. What algebraic expression can be used to describe the length? Let's just use a simple x. When we want to determine the width, we need to look at how x is related to the width. As I increase the length by 1, I'm decreasing the width by 1. But where am I starting? Starting with a value of 20. In fact, when I look at all of these pairs of lengths and widths, their total sum is always 20. 0 and 20, 1 and 19, 2 and 18, so on. So I somehow need to develop an expression that shows I've taken that length away. 20 minus x. What portion of the total perimeter is represented by the constant in our expression? This is critical because at the end of this, they're going to be able to determine an equation or an expression for the area given any size perimeter. Half. 20 is half of the total perimeter of 40. The total for one length and one width is always half the total perimeter. Now let's start looking at our areas. 0 by 20 is 0. 1 by 19 is 19. 2 by 18 is 36. And 3 by 17 is 51. At this point, students may have some trouble doing the calculations. That's fine. There's other ways to do it than straight multiplication. Since we know that this is a quadratic function, we can look at our difference of terms. Plus 19, plus 17, plus 15, plus 13. I can recursively add to determine the rest of the areas without doing a single step of multiplication. 51 plus 13, 64, 64 plus 11, 75, and so on. Again, students may notice that we've exhausted our unique areas the moment we get by 10 by 10. We do know that all of these areas are the product of the length and width, which means our area expression is x times the quantity 20 minus x. We want to ask students what shape gives us the largest area, and up to what point do we have unique area values. And the answer is a square, when the length and the width are equal. That's when we'll have the largest area. And up to what point do we have our unique areas? Well, it's from a length of 0 up to our vertex, or up to our perfect square of 10 by 10. After that, we may have slightly different lengths and widths, but all of the areas will be the same areas we've already observed in the first half of the table. We can now take this and use our experience to answer a question. A farmer is building a pen with fencing. The farmer has 38 feet of fencing and will make a rectangular pen. Write a functional equation to model the area for the length. We have 38 divided by 2, since we're only going to be talking about half of the perimeter when we look at length and width. That's 19. We know that our area is going to be the product of the length times and the product of the width. X times 19 minus x. That's it. That's all we needed to do. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.